Hi everybody. In this video I'm going to be going through the Further Maths AS mock paper in full. I'm going to try and go through it in a sort of like over-explained fashion, so if there's any questions that you were like, I have no idea how to do that, then this is hopefully going to shed some light on some of those areas. I'll break down the video so it's all time-stamped so that you can jump past question 1 if question 1 was completely fine. Before you actually watch these videos, it might be worth trying some of these questions yourself outside of the exam hall, outside of the timed pressure and sort of other general pressure that sitting in exam conditions might provide. Possibly try it with your notes as well, because it's always a bit of a nice boost to try a question afterwards and be like, oh yeah, I could have done that. Of course, there will still be areas where there's a lack of understanding, and that's okay. That's what the mock's for, right? We're going to see what it is we couldn't do and try and fix that. So without further ado, I'm going to go through the questions. Let's go. Okay, here's question 1, all about matrices and inverses by the looks of things. The very first part says that we've got two matrices, A and B, and they are given here. That's matrix A, 4, 2, minus 1, minus 3. Then we've got another matrix B, which is 4, 2, 1. First part says, explain why B has no inverse. Okay, let's break this down. So matrix has an inverse, and the general formula for an inverse matrix, say that the letters or the values in the matrix are A, B, C, D. The inverse matrix would be 1 over the determinant, and some of these elements get swapped around, and some of these elements have their signs changed. That's the formula for a general inverse matrix. So why does sometimes our inverse not exist? It's all to do with this fraction here. We're dividing by a determinant. You might remember that the determinant of a matrix is given by A times D minus, so that's what goes in here. The one thing that we can't divide by is 0. The determinant of a matrix is 0. Has no inverse. So let's calculate the determinant in the case of matrix B, see what we get. Got a feeling that it might be a 0. Write down the matrix B again. The determinant of B is going to be these elements, 4 times 1. Take away these two elements. And indeed, it does work out as 0. Because the determinant of B is 0, there is no inverse. Cool. B part 1 then, it's a 3 marker. It's asking us to find the inverse of the matrix A. So that's the general formula for an inverse matrix. We are being asked about the matrix A, which I need to remember is the matrix 4, 2, minus 1, 3. So A inverse is going to be 1 over the determinant of A, and I'm going to need to swap these elements. Positions of the 4 and the minus 3 are going to change around. And these elements have their signs negated. 2 and the -1 stay in place, but they become a -2 and a -1, which is a +1, of course. As for the determinant, formula for the determinant is A times D, the top left times the bottom right. Take away -1 times 2. I'm going to get here -12, take away -2 is a tidy this up a bit. Inverse matrix A is going to be 1 over -10 3 -2. And it's totally fine to leave your answer like this. That's the correct answer. If you did want to absorb the fraction into your matrix, call it something like this as well. So -3/10 over -10, so 3/10, 10th, 10th, -4/10. You can do that as well. That's totally fine. Or decimal equivalents, that's all okay too. So this part is sorted, and then we've got a 2 marker to finish it off. Find the matrix X. A times X is -4, 1. Okay, let's just write that down. The A times the matrix X gives us the result for -4, sorry, 1. And we know the matrix A oh, we don't know it off by heart. There it is. 4, 2, -1, -3. 4, 2. So that is the statement there. AX is -4, 1. So you might already be happy that the matrix X, it would need to be a 2x1 matrix. It needs to be that size in order to produce a vector like this. There's a few ways of doing this. You could set it up with simultaneous equations if you like. So you could say, I don't know what these letters are in the matrix, but I know that if I was to multiply it, 4 times A times B, and that would give the value there. You could make a simultaneous equation. And you could make something really similar by going through on the bottom line. -1 times A minus 3 times B is 1. And you could solve those simultaneously. However, there's something else that we can do that might be a little bit easier in some ways, especially because we've already worked out A inverse. What we could do is take this statement, let's write it again. The vector X, this is one that we don't know. What we're going to do is we are going to multiply both sides of this equation by A inverse. Oh, I do need to specify actually. I need to multiply it on the left. I want the A inverse to go here and here. The dog's crying incessantly, so I'm going to pause it briefly. Let's come back to it. Okay, the dog's gone. So I'm going to put A inverse on both sides of this equation. So A inverse was up here. There we go. So I'm going to take this matrix, I'm going to put it on both sides of this equation. Make a bit more space. In the same way as I can multiply both sides of an equation by a number, I can do that with a matrix as well. It doesn't fit still. There it is. And I can also do it on the other side. Oh, sorry about the faff. Copying and pasting and moving all that about. That's there now. So this doesn't really look easier at the moment. In fact, it looks kind of gross. I've made it more complicated, right? There's more matrices. However, what I've got over here is a matrix and its inverse next to each other. And the general rule of matrices is if you multiply matrix by its inverse, you just get the identity matrix, right? And that's something that you can verify. You can run it through on your calculator. Multiplying these matrices together should just give you the identity. And the good thing about the identity matrix is when you multiply by the identity, it doesn't do anything. It's the equivalent of multiplying by 1 with numbers, right? It doesn't do much at all. The right-hand side of the equation is still exactly the same. It's this thing here. But we'll be able to work this out. Multiplying by the identity doesn't do anything at all. So get rid of that completely. And we can calculate this multiplication. So tenths times minus 4 is minus 12 tenths plus 2 tenths. And on the denominator, it's going to be minus 1 times minus 4, which is positive 4 tenths. And then we get our vector out. Okay, here's a transformation problem. We've got two operations. We start with a coordinate. First of all, we transform it. We move it 2 across, 2 to the right and 2 down. And then once we've done that, we reflect it in the line y equals x. There's two things going on here. The first thing is just a movement. You start with a coordinate, move it 2 to the right and then 2 down. Just going to write that down as a bit of reinforcement. And then we reflect it in the line y equals x. Mirror line, diagonal mirror line, have a coordinate, mirror line, it gets mirrored like so. So we need to come up with matrices that do this. The general translation matrix is a 3 by 3 and it looks something like this. It's an identity in the top 2 by 2. It's 0, 0, 1 on the bottom, and then here have the values that we would like to move it to the left or the right. This number corresponding to the horizontal movement, and this one corresponding to the up and down movement. So in this case, we are going to have 2 and minus 2, right 2 and down 2. We've also got this one here. What it can be good to do to try and make sense of this, because I don't remember a lot of these memory. It's good to try it out with some numbers. Think this was a coordinate like 5, 1. If I reflected it in a diagonal line, where would it go? Hopefully you'll be able to spot that it would go 5. So if you're trying to work out what the matrix is, what numbers to put in here, you just need to think about how this is going to multiply. You need to do something times 5, then something times 1. It gives you 1. You need there to be a 1 there and a there. So you can kind of work out what the matrix needs to be by sort of following this through. Something really similar on the bottom line as well. Something times 5, something times 1 equals 5, 1 times 5. That matrix here is the thing that's doing my reflection. And in order to make it so that it works with the other matrix, the 3 by 3, there it is. What I need to do is just put a row of zeros and ones around it, like so. One, zero. Then the other elements are zeros. I also need to think about the order in which I need to multiply these matrices. Because it's a translation first, followed by a fraction. What I need to make sure happens is when I'm doing my multiplication, I have my coordinate, whatever it is. I do the translation first. That is the matrix that's immediately next to the coordinate. And then I do the reflection. So what you might remember is it sort of builds its way outwards to the left. Okay, let's put these numbers into these matrices. That's my translation matrix. And this is okay, cool. My cool part of it. So I'm going to multiply these matrices together. Leave loads of space for my workings. So if I wanted, for example, the top left element matrix, I would need to take the top row and the left column. What I'm going to be doing here is 0 times 1, 0, 1 times 0, 0 times. That's going to be my calculation going through it. So it's 1, 0. That does result in a 0. Top. Yeah. When I'm doing this, I'm just scanning to see anything that isn't like 0 times something. So I'm looking like here, for example, I've spotted that's a 1. That should just be my matrix T. So part B is talking about fixed points. So what are they? When you do a matrix transformation, have a coordinate, and it might move it or transform it in some way. A fixed point, when you multiply a matrix by a coordinate and nothing happens at all. Kind of like if this was the identity matrix, obviously nothing would happen, but this matrix is trying to do something. It's just that it doesn't affect that coordinate. You can think about it as if your matrix was, let's say, a reflection in the line. Yeah, let's just use the one that we've got actually. We've got a reflection in the line y equals x. So if you had a point down here, then yeah, sure, that's going to be reflected. But if you had a point that is on this line, it's on the mirror line, then it's not going to move. So what we are being asked to work out here is you have this matrix, which represents 2 different transformations at a time. What are the fixed points? Maybe there's just one, maybe there's more than one. We'll see. We're going to say for any coordinate x, y, put a 1 in just so that we can calculate a 3 by 3 equation. If it's a fixed point, then nothing should happen to it. It should stay exactly the same. We're going to multiply out this left side, and we're going to see what it works out as. So we're going to do 0 times x, 1 times y, minus 2 times 1. We are going to get for the top line plus y, take away 2, result of the first multiplication. The middle row is going to be 1 times x, 0 times y, and the bottom row is going to be and you can think about these as two equations. First row represents one of the equations, the second row another equation, and then the equation at the end, 1 equals 1. Well, you're like, yeah, that's true, I guess, but it doesn't really help. These two equations, you might notice with a little bit of rearrangement that they are exactly the same. So if you take that minus 2 over to the other side, then you would get equals x. This equation is x plus 2 equals y, and you see that they are the same thing. So what we end up with is the line x plus. This mean? Essentially it's saying you started with a coordinate that was on the line y equals x plus 2, and you did these two procedures. You moved it to the right 2, then you moved it down 2, and then you reflected it in the line y equals x. Then it would end up right back where it started. And that goes for any single coordinate that is on this line, y equals x plus 2. So any point on the line y equals x plus 2 is a fixed point, and there are infinitely many of those points. So going back to the question, we have an infinite number of fixed points. Hello, we are back at it. Here is question 3. This time we are still looking at matrices, and there seems to still be things to do with determinants and something about singularity as well. So first of all, let's have a look at part A, which says find the determinant of the matrix A in terms of A, which essentially just means that we're expecting this little a to show up in our final answer. So once again, for any matrix, the determinant of it is the top left and bottom right elements multiplied together. Subtract the product of those other two elements, AD minus BC. So in the case of the matrix A, where we've got A minus 5, 2, A plus 4, we're going to go ahead and calculate the same multiplication. We're going to multiply these two things, A and A minus 4, and I'm just going to write it in its bracketed form. And then I'm going to multiply these two things, minus 5 and 2. And immediately I'm noticing that I'm going to have like a double negative situation from this minus 5. So let's expand the brackets. A times A is going to give me A squared. I'm also going to get a 4A from the next multiplication. And minus minus is A plus, and that's going to give me a plus 10. And I think that's as far as I'm going to go for the determinant calculation. That looks pretty good to me. Smiley face. So let's have a look at part B. This thing here, part B, says show that the matrix is non-singular for all values of A. So, singular means that the determinant of the matrix is equal to 0. So non-singular means essentially not that. The determinant of the matrix is not 0. And I guess we're talking about the matrix A, so I'll just put that straight in. So we've got the determinant, which is A squared plus 4A plus 10. And we're supposed to show that this cannot be equal to 0. It doesn't matter what number we put in here. There's no way that we'd be able to get 0 out. There's a few strategies to this. You might think about a bit of an analog to something that you've done in AS maths, which is the discriminant. So this is a sort of quadratic equation, right? So we could use quadratic equation techniques for it. I think that's what we can do. We'll try and solve it with the quadratic equation. I'm gonna use the letters A, B, and C for this, but I'm referring to the constants in front of A squared, A, and the number on its own, of course. So write the quadratic formula down as if to solve this. So that's what the solutions would be. In this case, I've got A as 1, B as 4, and C as 10. So if I was to plug all those things into this equation, I'd have minus 4 plus or minus square root 4 squared minus 4 times 1 times 10, all divided by 2 times 1. Wonderful. I'm not even going to use the calculator, guys. That's how confident I'm feeling with this question. Okay, so what's going to happen here is our square root 16 take away 40 is going to give us a negative result. So if you were thinking about a discriminant root, you were just thinking about this formula without thinking about the quadratic as the whole, you probably already know where this is going. So the minus 24 in the square root tells us that there are no real solutions. Essentially, if we're trying to solve this equation, the only possible answer there would be for it would be a complex answer. There's no whole numbers, there's no real numbers that we can substitute in there. Or a whole number, it doesn't have to be a whole number, but there's no real numbers that we could sub in there to make it work. It would have to be a complex value. There we go, that shows it. Therefore, the matrix is non-singular for any value of A. Is the matrix section all sorted? Question number 4. Complex numbers with some weird constants. We've got z equals 3 plus lambda I. So it's a complex number. We're told the real part, we have a constant for the imaginary bit. So that's what we're dealing with. We are given an equation as well. Z squared plus z conjugate squared is 2. So just that notation, first of all, makes sense of it. We know that z is equal to 3 plus lambda I. Hopefully you're familiar with this notation. means Z conjugate, and practically what that means is the real part stays the same, and we change the sign of the imaginary bit. So Z conjugate is going to be 3 take away lambda I. And I think essentially I'm going to just substitute these things into the equation. I'm going to replace Z with 3 plus lambda I, and I'm going to square that. I'll replace Z conjugate with this thing. I'll set it equal to 2, and I'll try and solve it, and we'll see what happens. Let me write down this equation. It is Z plus Z conjugate. Both of these things are squared equals 2. And I'll start by replacing Z with 3 plus lambda I, and Z conjugate with 3 minus lambda I. There we go, fantastic. Those things have been replaced. What I'm going to do next, because they're both being squared, I'm going to write them as double brackets. And they're both going to be kind of similar to each other, so I'm hoping that there's going to be some cancellation or something good going on somewhere. Let's file this out. So we're going to get 9 plus 3 lambda I plus another 3 lambda I plus lambda squared I squared. This file over here, let's just highlight that. That's the result of the first part. The second part is going to be 9 minus 3 lambda I minus another 3 lambda I minus a minus, this last term, the plus. So that is going to be plus lambda squared I squared is equal to 2. Cool. Right. What next? I guess. Oh, I didn't mean to delete that. Move it up a bit. I'll do that. Never mind. I guess we can cancel things. So, see, these numerical terms on their own, they're not going to cancel. So I'll just combine those together to give me 18. The other bits, though, these imaginary bits, 3 lambda I, that's 6. Take away 3 lambda I, take away another. They are all going to cancel out. They're all gone. Great. And I've got these two terms here, lambda squared I squared, and I've got 2 of them. I'm just going to write that as is at the moment. And I'm going to be solving for lambda eventually, so I'm thinking to make this the subject. There's also something that I can do with this thing here, though, I squared. I'm sure you guys know this one. I is defined as the square root of -1. So I squared is equal to -1. So I'm thinking to replace that. So let's do that. 18 plus 2 lambda squared instead of I squared, -1. And let's just tidy this up a little bit. Fantastic. And we can go ahead, rearrange it and solve. Let's take the 2 lambda term over to the right hand side. Let's take the 2 over to the left side and subtract. And we are going to get a value of 8 for lambda squared, which means that lambda could be plus or minus 8. But I need to pay attention and read the question again just to make sure that I'm on the right lines, because I skipped through this bit. It tells us in the question that lambda is a positive constant. And if it's a positive constant, then it can't be -8. Therefore, we choose the positive value, and we've got lambda as √8. Ooh, good question, that. Okay, question 5, and I feel like this is quite a difficult one to make sense of, especially if there's parts of the topic that you don't really like. So I'm going to cover a tiny bit of theory, I suppose, here. When you have the modulus symbol like this, essentially it's calculating a distance from a certain point. And if it's just z on its own, it's calculating a distance from the origin on an Argand diagram. Okay. And the formula for the modulus is just the distance formula that you know and love. Good old Python. So you see how far you've gone across the x value, you see how far you've gone up, and then that gives you that distance there, which is what we want. If you have a slightly different version, like maybe you have this z take away 1, it still calculates a distance for you, but essentially what it does is it recenters it, right? It becomes a distance from the point 1, 0 instead. You take that point there, 1, and you're working at a distance from there instead. So you still have an x and a y value, but the formula looks something like this instead. What I'll do, I'll split this up into an x and a y, and I'll combine the real parts of it. So when you work with the distance formula, you're just dealing with x minus 1 instead of x, right? And the y part of it still stays the same. Right? You just have a look at that bit and calculate the distance there. Right? So when we are calculating a modulus, when there's something like a little bit different, you're essentially using the distance formula with a adaptation of some kind. Your x and your y arguments just change a very slightly, they change. With that in mind, let's try and make sense of this question. We've got a complex number z. It's represented by a point on the Argand diagram, and then they give us this equation with some serious modulus stuff going on. So it satisfies this equation. Show that the locus of P is a circle, and write down the coordinates of the center of the circle. Okay. So starting to make sense of this one then, like I'm going to write it down quick. Z minus 3 plus I in a modulus, and 2 lots of Z minus 5 minus 2I. So first of all, the thing I'm going to do is I'm going to replace the Z's with X plus IY's, just so I can have some separation of real and imaginary terms. I'm going to write them both as X plus IY. And the next thing I'm going to do is I'm going to combine the real and imaginary parts. I'm going to just move all this stuff out of the way from earlier on. There we go. See you later. And let's group these things together. X minus 3 and IY and I look something like this. X minus 3 plus I brackets Y plus 1. Let's do the same thing on this side. It's going to be a X take away 5 and an I brackets Y minus 2. So this thing over here is going to be looking at the distance from the coordinate on the Argand diagram 3 minus 1. Something else that you can link it to, which might be useful, is the idea of a circle equation, right? When you have the center of a circle, you can work it out by reversing the signs in those brackets. It's the same principle in this case here. This is representing a distance from 3 minus 1. This is representing a distance from 5, 2. And this equation says that the distance over here on the left-hand side, the one in green, that distance should be 2 lots of the other distance. Okay, so the distance from the thing underlined in green should be twice the distance of the thing underlined in red. And I've made a quick diagram to show what this looks like because it's weird. It's an abstract thing that we're looking at here. So the thing that I've got in blue, I should match up the colors really, shouldn't I? What colors did I have? I had green and red. What was it again? I've forgotten. Let's go back. The distance from 3, 1 is blue, and the distance there is green. There we go. Right, so I just to underline it, I've got the colors right this time. This is what's going on. We're trying to figure out all the coordinates for which this distance is double that distance. And it turns out there's a bunch of coordinates that satisfy this rule. So notice the numbers in the distance equation up here, they always stay double. Notice that it's tracing a circle. And the goal here is to find out what that circle is. That's what's going on in this question. So I'm going to try and convert both of these into the distance formula, essentially. So this is going to turn into x minus 3 squared plus y plus 1 squared. And the thing in green is going to turn into x minus 5 squared plus y minus 2 squared. Notice that going from this step to the next, the i's have been dropped completely because we've gone from coordinates that are in an Argand diagram to purely thinking about distance. So when we use the modulus formula, we don't include the i's in any part of that, right? They're just gone. Right, this is what we're dealing with now. Two distances related in this way. The square roots don't look very nice. So I think the immediate plan would be to get rid of the square root terms. And we do that by squaring. We're going to square both sides. So when we do that, if I just copy and paste this, I'm going to square both sides. And as you guys probably know, the opposite of squaring is square rooting. So these terms are just going to cancel completely. Oh, wonderful. See you later. The thing I need to be a bit careful of is square root will cancel here, but there's also another element. There's also this 2. So what I'm going to need to do is distribute this power. So it's going to become 2 squared multiplied by this square root squared. Of course, the square root and the square, they cancel, leaving me with a statement something like that. So now I've got rid of all of the complex bits. I should be able to do some foiling and a lot of tidying up. Let's write these as files. Let's write these as double brackets. Here we come. Right, here we go. Let's start expanding these brackets. Lots of algebra to do in this case. I'm going to deal with the 4 afterwards. Will I be able to fit all this in? That is a good question. We'll find out. Definitely making my writing smaller, that's for sure. Just about. Right, let's combine some terms. We've got x squared take away 6x. Let's put the numbers at the end, that'll be fine. Plus y squared plus 2y plus 10. That's the entirety of the left side. Right hand side is going to be x squared take away 10x, y squared minus 4y, and the numerical bits are going to be 25 and 4, which is 29. And I think now I'm going to multiply through by 4. Give something like this. Make sure I times everything by 4. 29 by 4. Can I do this? Yes, 116. Wonderful. All right, lots to write down here, isn't there? Ooh. I guess I know that eventually in this question I'm supposed to get the equation of a circle or something to do with a circle. So what I'm thinking is I need to eventually get it to look something like that again. I need all the numbers to be on one side, and I want all the other bits to come on the other side. That's the plan. So let's try and simplify it. Everything over to the right, I guess, just so that the x squareds and the y squareds will be positive. So take away all of this stuff. Oh, right, x squareds first of all. 4 take away 1 is 3. X is next, minus 40, take away minus 6. Sure to not mess up the signs. All right, it's 34. The y squared terms should be easy enough. 4 take away 1 is 3. Minus 16 take away 2 is minus 18. And the big numbers, 116 take away 10 is 106. Okay, does this look like a circle yet? Maybe. you might have seen versions in regular AS Maths looking something like this, you know, like all of the terms expanded out. You might have seen a version like that without 3's in front. So what we could do is divide it all through by 3 to make it look a little bit more circly. So let's do that. X squared 34 over 3x, not a great number, plus y squared, take away 18 over 3 is 6. 106 over 3, does that go in? No. This is 106 over 3. Okay, gross, but it is actually getting there. Does resemble a circle a bit more. The next thing I'm going to do is I'm going to complete the square for these parts. So it looks a little bit more like a circle again. The basic premise for completing the square is just going to be half in that value there. So it's going to look something like this. X minus half of 34 is 17. Ooh, I didn't half that. Sorry, half of 6 is 3. And it's still equal to 0. Cool. So that is pretty much sorted in terms of the circle. I wouldn't be able to read off what the radius is. I'm looking at the question. I don't think I need to. So it's a little bit lazy. I'm supposed to write down the coordinates of the center, which I can get by just reversing the signs here. The center of the circle is going to be 17/3 for the x, 3 for the y. And if I did do a little bit of tidying up here, which I can be bothered, then I would be able to get a radius. I'd get the value of r squared from merging these 1, 2, 3 terms and taking them over the left side. Hello, question number 6. Now I have to start using 2 hands. Indicate the number of the question. We've got a complex number which is some sort of fraction, and we need to calculate the modulus and argument of it. It's worth 8 marks. There's so many marks. So this is kind of like a 2-part question. The first part of it is to attempt to simplify what we have in this fraction. We've got like a double bracket along the top of it. There's going to be some expansion to do there. We also have an imaginary part on the bottom of the fraction, which means that we're going to need to rationalize, sorry, not rationalize, we need to get rid of the complex part on the bottom through some clever simplification. So what we'll do, I'm just going to write this down as it is to begin with. I think I'm going to start by multiplying the 2 brackets on the top of the fraction. I think that sounds like a good plan. Let's expand these brackets first of all. So that's going to be 1 times minus 3, 2 times 2i times minus 3, 1 times I, and 2i times I. And like we mentioned in an earlier question, I squared equal to minus 1. So if I replace this I squared with a minus 1, I'll be able to combine it with this numerical term as well. So a little bit more tidying up on the top. If I combine the real parts, I'm going to get minus 3 take away to minus 5. And the imaginary parts, I'm going to get minus 6 plus 1, also minus 5. Hey, this looks a bit nicer, doesn't it? Cool. That's some progress. What we're going to try and do next is to get rid of the complex part, or the imaginary part, for this number. And the way we're going to do that is we're going to multiply by the complex conjugate. I'm sure you've seen this idea before. You do a similar thing in surds to get rid of any square roots on the bottom of a fraction. I'm going to take this fraction and I'm going to multiply it. I'm going to move it so it's on the line. I'm going to multiply it top and bottom by the conjugate of what's down here. So we've currently got 1 plus 3i. I'm going to multiply by 1 minus 3i, top and bottom. This is going to be a double FOIL again. I have this multiplication to do, and I'm also going to have this multiplication to do. So let's try and deal with the top of the fraction first. We've got minus 5 times 1, minus 5i times 1, minus 5 times minus 3i, which is plus I. And then finally, minus 5i times minus 3i. So there's a few things going on here. Minus times a minus is a plus. I times I is I squared. Will eventually change to -1, and we'll group two bits together. Let's also expand the bottom while we're here. We're going to get 1 plus 3i minus 3i take away 9i squared. Keep in mind the reason why we're doing this is for this to cancel. So if you can see a change of sign like that, we're onto something. This is looking good. All right, top of the fraction. As we mentioned earlier, this is equal to -1. Let's change it. Here, -1. And that's going to give me -5, -5, take away 15 on the top. Don't really know why I needed the calculator there, but we've got -20. And these terms, the imaginary ones, 15 take away 5 is going to give me plus 10i. Bottom of the fraction, two terms in the middle cancel out. We have 1 take away 9i squared. Once again, I'm going to replace I squared with -1. We've got 1 take away -9. I feel like when things like this happen, when you've got a multiple of 10 everywhere, that's quite a nice feeling. It's like confirmation, I've probably done this right. So I'm going to break this into two fractions. They're both divisible by 10, so this is the sign. -20 over 10 is -2. 10 over 10 is 1. Of course, we can just call this -2 plus I. So that's looking great. That's the division part of it sorted. That's most of the marks. I think it's an 8 marker. I think that's 6 of the marks. Quite a nice set of marks there. Still this thing to do. Determine the modulus and the argument. So to do that, I'm going to quickly draw an Argand diagram so I can see where the complex number is. So -2 plus I. This is the real axis. This is the imaginary axis. -2 plus I is going to be back here. And the modulus is measuring how far we are away from the origin. It's measuring that distance there. And you can think about this as a Pythag problem. The distance that we're going across from the origin is 2. And the distance we're going up is 1 imaginary unit. Oh, well, I say that 1 real unit, but we're on the Argand diagram. So calculate the modulus with x squared plus y squared, where x and y are the horizontal and vertical distances travelled. I keep my answer as just √5. The argument is a little bit more nuanced, to do with angles, but it's not the angle what a lot of people do. It's not this angle here. A little bit more to do. Let's keep that in. The argument is the angle that you get if you start on the real axis and you go anti-clockwise around the axis. So that is the argument of our complex number. What we're going to do, we will find this angle, we'll find it in radians, and then we'll do some angle facts to figure out what that angle is in pink. So to get this angle here, I'm dealing with a triangle where I know the adjacent and the opposite, so I can use and. And I've forgotten what the tan formula was. It's opposite over adjacent. Oh, that's no good. So for the argument, what I'm going to do is find this angle here. That side's 1, that side's 2. Get the angle, I'm going to do inverse tan of the opposite. Ah, no, it's not that way around. So to find the argument, find the angle in blue here. What I'm going to do is just draw a smaller triangle. This side was 2, this side was 1. This is a situation where I can use trigonometry. Specifically, I can use tan because I know the opposite and adjacent. I'm going to get that tan theta is 1 over 2, and the angle is inverse tan of a half. And I can work this out. I'm going to make sure that I'm in radians before I do this. So I've got the inverse tan of a half. 0.46 radians. That is the angle here. That there, let's get rid of some of these other bits. That is 0.46 radians. But the thing that I want to get is here. So the fact I'm going to use is the fact about angles on a straight line, which in degrees would be 180 degrees. In radians, 180 degrees is pi radian. So to get this angle, I'm going to do pi take away 0.46 rather than 180 take away whatever it would be in degrees. Same principle, right? So pi take away there. Going to give me an angle of around about 2.68, some other decimals. I think what we'll do is we'll round that to 2 decimal places. Give 2.68 radians. Write it down here. Well, so the argument, my complex number, I take away 0.46, which came out as roughly 2 radians. Quite a lot of work to do for that last mark, but I would say argument and modulus seem to come up quite a lot, so it's worth getting your head around. Cool, that's another question done. That's the complex section over. Capiche? Hello everybody, we're on question 7 now, and we're on to the stats part of the paper. Here's a question about discrete random variables. This is a random variable where we can get any of the numbers 1, 2, 3, 4, 5 with differing probabilities. And the first question is very standard. They're asking for us to calculate a mean and a variance. So the mean, sometimes referred to as the expectation when we're talking about discrete random variables, can be calculated by multiplying all of the x values by their corresponding probabilities. So 1 times 0.1, 2 times 0.2, so on, and then we're going to add all of those results. So we can express it with this formula. It's the sum of the x values multiplied by their probabilities. We add them all together and we see what we get. This is going to work out as 1 times 0.1, 2 times 0.2, 3 times 0.3, 4 times 0.1, and 5 times 0.3. All of those things get individually added together. I think this is one for the calculator this time, but I think what I'll do one more step where I just write them out and see a terrible mistake where I've written a times instead of a plus. I would go poorly. There we go. Something to keep in mind with the expectation, it's literally, on average, what value do you expect to get, right? So I know that you can score values between 1 and 5. So the expectation should be a number between 1 and 5, probably towards the middle, maybe slightly on the higher end because the probabilities of 5 and 3, they're a little bit more likely. So let's add up these values. One for the calculator, I think. 5 things to be added. No chance. There we go, 3.3. That seems quite reasonable to me. We'll go with it. Next thing was the variance. And there is a formula for the variance. Looks like this. This is always quite a strange formula because it's pronounced EX squared take away EX squared. And then you think momentarily like that's the same thing twice. Not quite. This is the thing that we calculated just now. This is the 3.3. So we do end up squaring that 3.3. This thing, the expectation of x squared, is similar to what we just did when we multiplied the x values by the probabilities. But what we are going to do is we are going to square all of the x values first. And then we are going to, I'm trying to rub this out. There we go. Do it like that. So that's easier. We're going to square all the x values, then multiply them by the probabilities. So let me just get this table again. The x squared values are going to be 1, 4, 9, 16, 25. We are going to multiply these numbers by the probabilities. And we're going to see what we get. So the ex squared part, I'll write it out as if I was in an exam, I suppose. So it's going to be 1 squared times 0.1, 2 squared times 0.2, 3 squared times 0.3, 4 squared times 0.1, 5 squared times 0. Lots to type in and work out there. I think it's going to slam right in the calculator as that this time. Right, maybe I should have, I don't know. Right, there we go. That is the value of ex squared. So now let's go back to the variance formula, which was the variance of x is expectation of x squared minus expectation of x cos squared. This is going to be equal to 12.7 that we just worked out minus 3.3 squared that we worked out earlier on. And another one for the calculator, to be honest, take away 3.3 squared. What's that going to come out as? 1.81. One thing I'll say about variance to help you keep track of things, variance measures how spread out things are. It should always be a positive quantity. It'll be equal to 0 in the case that every single value is exactly the same. You can only get one value out. Otherwise, it'll be a positive amount. So this seems quite reasonable. Let's have a look at part B. Get the table again. Part B says that there's 3 independent observations. Essentially, like you run this probability distribution 3 times. So imagine this is like some sort of weird dice, except there's only 5 numbers on the dice. and all the scores, they're not equally likely to happen. So you roll this bizarre imaginary dice 3 times, and you work out S, which is the sum of those 3 scores. Right? You roll 2 dice in board games, right? Like Monopoly or whatever. This is kind of along the same lines. Roll this 3 times. Try it out 3 times. We're going to try and work out the probability that you get a score of exactly 4. If you really wanted to, this could be like the worst probability tree of all time, where you have 5 branches, another 5 branches, and another 5 branches off each root, and it would be a probability bush. It would be dense, you know. So we're not going to do that. But what we can do is we can imagine how we can get a total score of 4 from 3 observations. Because there's not actually that many ways it could happen. We could get on the first roll. We know we can't get 4 because we need to roll again. Similarly, we can't get 3 either because that would give us a total score of 5. So the only way that we can get a 4 is if we have a 2, a 1, and a 1. That's the only way we can make a score of exactly 4. We will need to think about the other permutations of that. So if you score a 2 first, or whether you score a 2 second or third, those would be sort of equivalent possibilities. So that's one thing that could happen. But equally likely is this or this. Those are the 3 ways that we could get a score 4. So to calculate something like this, we would just multiply probability of getting a 2 by the probability of getting 1 by the probability of getting 1 again. It'll be 0.2 times 0.1 times 0.1. It'll be 0.002. That is that one possibility here. Because there's 3 different ways that this could happen, we are going to multiply this probability by 3. And that gives us the probability of a score being exactly 4. It seems okay. The last part of this problem throws an inequality in the mix. And it says that the score could be 4 or less. So I'm just, again, thinking of how many scores you could get that are less than 4, right? There's not many. The lowest score that you could possibly get would be getting 3 1s, right? That would be a total score of 3. There's no other scores that you can get less than 4, either 3 or 4. So the probability of the score being 4 or less is the probability of the score being 4 plus the probability of the score being 3. We've already worked this out. We just need to work out the probability of the score being 3. Roll in 3 1s. Just be the probability of getting 1 times itself 3 times. I think we are going to get 0.007 from that. Nice. Hello, question 8 this time. We are talking about properties of expectation and variance. So what I'm going to do is I'm just going to note down some key formulas for this. The expectation of a joint distribution like this can be broken down to be a times the expectation of x, expect y. If you have a constant as well, you can sort of split that constant out and work it out like that. The variance I believe the rule is that we square any constants. It looks something like this. I need to take some more space here. If we have a constant, it does not do anything. Variance. I think the one other thing that we need to be aware of is if you are subtracting something in a variance expression, you still end up adding. It still increases the overall variance whether you're adding or subtracting two solutions. So those are my facts. Some of them might be in the formula book. I'll have a check in a bit. Hopefully all of that information will help me proceed. I suppose there's one other thing which we used on the previous question, is this thing here. So that might come in handy for some question. Have a look at part A. We've got the expectation of 4y take away 2x plus 1, and x has a mean of 17 and a variance of 4. Y has a mean of 10 and a variance of 16. So this expectation formula here can be split into 4 lots of the expectation of x, take away 2, oh sorry, got the letters wrong straight away, that's a y. 2 lots of the expectation of x plus a 1. So when it says mean, that's essentially telling me the expectation, right? That is the value of expectation of x and expectation of y respectively. So I can replace the expectation of y with a 10. I can replace the expectation of x with a 17. And I can tidy this up. I'm going to get an expectation of 7 from this statement. The next one is a variance statement. It's the variance of 4y minus 5x plus 3. The first rule I'm going to use is this one here when we're dealing with constants. We have a plus 3, it's like it's not there at all. That's just gone completely. The other thing I'm noticing is there's a minus in the bracket here. So when I split this up, I'm going to have to add the expressions rather than subtracting them. And of course, I've got constants in front of x and y, and I'm going to have to square them when I pull that out. It's going to look something like this. 4 lots of the variance of y. Oh, no, 4 squared times the variance of y plus 5 squared the variance of x. And that's 16. And I've added a bracket for some reason. Let's get rid. Do I know the variances? Yes, I do. The variance of x, up here, it's 64. The variance of y is 16. So I'm going to replace both of those. This is going to be 16 lots of 16, 25 lots of 64. We're going to do some number work. Not going to try and do 25 times 64. I think it's 1600 actually. Yeah, I should have braved the storm, guys. Add the 256 on. go. That is my variance calculated. Have a look at C. Got the expectation of x squared times y. Right, that's a bit weird, isn't it? Let's try and break this down. So I know that they are independent variables. Means that I can split up the expectation of the x parts and the expectation of the y parts, like so. I know the expectation of y, that is 10. Oh, this is 10. It's tempting to call this 17 squared, and it's not. I think what we're going to need to do is use some variance ideas for this one. So what I know about the x squared is it makes up the variance formula. It's part of it. Specifically, the variance of x is equal to the expectation of x squared, take away the expectation of x squared. I know the variance of x, if I scroll up, is 64. And I know that this is 17. So I'm going to do a little bit of rearranging to get the value of the expectation squared. 353. Cool. So now that I've got that, question can proceed, and it's quite nice now working out that last part. Yeah, something to be careful with. I think it's one of those, when you've seen lots of expectation questions, it's something that you grow to kind of expect. They're kind of trying to catch you out. But yeah, that's that question done. That's the stats section. Capiche. Finished. Bonjour. Bienvenue dans la section mécanique. I recorded this question and, well, I thought I recorded this question and nothing saved, so I'm going to get rid of all my workings. Maybe I'll keep the cyclist actually, because he's cool. And I best record it again. So we have got a little bit more to get rid of first of all. This is devastating, guys. Let's move this over there. Get the question back, and let's make sure the cyclist can be seen. Fantastic. Right, back at it. So this is a situation where we've got a cyclist on a mountain bike track, and we are given the heights above ground level for A and B, 20 and 22 meters respectively. So what I'm doing here, I'm immediately thinking about energy and thinking they gave me those heights because that's going to help me calculate GPE. So that's something I've got in my mind. We are also told the length of the track between A and B, that is 16 meters. That is the distance traveled here as he goes along this sort of curved path. That is 16 meters in total. We are also told that there's a resistance which has a constant magnitude 50 newtons, and later on we're told that the mass of the bike and the cyclist is 70 kilograms. The speed of the biker is v at the point A, so over here cyclist is moving. Again, I'm thinking about types of energy. I'm thinking he's got some kinetic energy. Find the minimum value of v if the biker is to reach B without pedaling. So without pedaling means there's no additional energy coming from the cyclist coming into the system. We want the cyclist to get to B, goes all the way up there, without adding any extra energy into the system. What I'm also thinking is if he's going to reach B without pedaling, I want to find the minimum value of V. So really, I want him to like get to B, basically like stop right on the top of the hill, so like no extra energy is expended. I want the absolute minimum speed that he's traveling at this point to just about get here. Leaving part of my bike behind. So with all that in mind, here's my setup. This definitely seems like an energy problem to me, just on the information that I was told about heights and speeds and resistances. So that I'm going to write down the energy at A equals energy at B equation. I know that at A, there's definitely some potential energy because I know a height above ground. And I also know, because the cyclist is moving at the point A, there's some kinetic energy. Because the cyclist isn't pedaling, there's no additional energy in to consider here. But if he was pedaling, that's where it would go. Over at B, know that there should be some GPE because he's actually higher up than he was before. I know that there isn't any kinetic energy because I want him to get to the end like just about. I want him to stop when he gets to B. However, I know that the cyclist is experiencing a resistive force. So some of the energy is going to be like dissipated, I suppose, used to get over the resistance. There's going to be some work done versus resistance. So let's plug in everything I know. I know the GPE formula is mgh. I know the mass of the cyclist and the bike. I know gravity, and I know at A, he's 20 meters above ground level. The kinetic energy, I know the formula is a half mv squared. I don't know the velocity, but I do know the mass, so I'm just going to have to leave that as it is. It's fine. GPE at B, same formula, except the height is 22. And all of these quantities so far have been amounts in joules. So we want to keep that consistent. We want to make sure that this is an amount in joules as well. Something that I noticed, a common mistake with this, is people said, oh, he's going to use some energy against resistance, and I know the resistance is 50, so I'm going to put a 50 there. But keep in mind, this is a 50 newtons, and if we're comparing those quantities, it's apples and oranges then, right? We shouldn't have an equation with more than one type of unit in it. So that might jog your memory to work done, which does produce a quantity in energy terms, then in joules. That is going to be the force, which is 50 newtons, multiplied by the distance traveled along the curve, 16 meters. And that will give indeed a quantity in joules. So when I zoom out on this, almost everything, apart from V, which I'm going to need to work out, I know every other quantity I have a numerical value for it all. So into the calculator it goes. Write that one down. This is going to be 35 V squared. I'm going to change this 20 to a 22. All right, let's try and get V to be the subject of the formula. So let's take this number over to the right-hand side. And let's see what this comes out as. 2172. And then let's divide through by 35. And finally, see the remnants of my smiley face from the last time I tried this question. I'm going to square root it. Get that the value of v is around 7.88. Two decimal places. I'm going to add the i's back in. I'm going to make them evil. Why not? Oh, but I am going to... How could I forget that? That's terrible. Okay, question 10. Last question of the paper. And what a question to finish on. Lots going on here. Let's have a look at what we've got going on. Lots of text. We've got two objects. Sorry, I've just frozen in time. We've got two objects and they are rolling. I'm looking at these speeds. They're not going to collide at the moment, but that's okay. We'll see how it plays out. This first sphere, sphere A, has a mass of 3 kilograms. I'm just going to indicate that on the diagram somewhere. And sphere B has a mass of 2 kilograms. Ah, right, okay, I'm reading this next bit of text here. Sphere B is then given an impulse, after which it moves in the opposite direction with speed 6 meters a second. So this is my before. And then something's happened to sphere B, and now it's going the opposite direction. Let's just make a really quick new diagram. What's going on? Sphere A is still doing its thing. It's still going this way, 4 meters a second. The weight hasn't changed. It has not dieted since, well, since here. And we've got a 2 kilogram mass, and now it's traveling in the opposite direction at 6 meters a second. So there's definitely going to be a collision very soon. Right, let's have a look at what we actually need to work out. I haven't even got that far yet. Calculate the magnitude and the direction of the impulse exerted on B. So the impulse is the change of momentum. So this is what I'm thinking. It's the momentum after, take away the momentum before, or the other way around. It doesn't really matter. And momentum is the mass times the velocity of an object. So the mass of object B is 2 kilograms. So I'm going to replace both of the masses with 2's. The velocities are 6 and 10, but something I need to keep in mind is the directions have changed. So when I sub in B and U, I need to take that into account with a sign change. So if I say that the right is positive, then I would have -6 and a 10 here, for example. It doesn't have to be that way around. If you do it this way, you get -32 out as your impulse. So I suppose the magnitude of the impulse the size of the number is 32 Newton seconds, and the direction of the impulse is, I guess you could say it's to the left or the opposite direction that it was originally moving. Okay. The reason why we have to state this is there could have been 32 Newton seconds of impulse exerted on that object, and it might have been like going much, much faster in the direction to the right. So we have to be careful. We have to state that. I think now this is our situation. These objects are going to collide. Case of when. And we're going to see what happens next. So over here, sphere B continues to move with speed 6 meters a second so that it collides directly with sphere A. The kinetic energy lost due to the collision is 45 joules. Oh, that's weird. See that very often. So VA and VB represent the velocities of A and B after the collision. Show that by conservation of momentum, 3VA plus 2VB is 0, and that energy loss may be expressed like that. So this is like two simultaneous equations, but we have to derive them. We have to figure out where they come from. So the momentum formula, conservation of momentum, is the momentum before a collision is equal to the momentum after a collision. So this is the situation just before the collision happens. And I'm going to draw another diagram like this. Let's make more space. So this is before. And afterwards, I don't know what's going to happen. I have no idea. But I know the speed of A will be VA, whatever that is. And the speed of B is going to be VB. Now, I don't know whether this object is going to be going to the left or the right. But for ease of calculation, I'm going to assume it's going to the right. And yeah, we'll just see how that all turns out, I suppose. So the momentum before for object A would have been 3/4 mass times velocity. The momentum of B would have been 2 times -6 because the direction is to the left. The momentum after for object A will be 3 lots of VA, and the momentum for B will be 2 lots of B. So that right-hand side looks good actually, because that is what I needed. So if I just work up this side, it does indeed give me the formula straight away. So that's kind of good. That's one of the formulas in the bag. Another smiley face. The other formula looked a bit weird. Energy loss. So they told me that the kinetic energy lost was 45 joules. So this is what I'm thinking. I'm going to calculate the kinetic energy before by having a look at how much energy A and B had. So for A, the kinetic energy would have been half mv squared. Mass is 3, and the velocity is 4. And then for B, half mv squared again. The mass is 2, and the velocity is -6. It's going to be squared, so it won't matter. That's the total kinetic energy for A and for B. Let's add these things up. We'll just chuck this in on the calculator. Let's persevere. 4 squared is 16, times 3 is 48, half is 24. And this one, 6 squared is 36, 2 times by half is still 36. So there's 60 joules worth of energy before the collision. I know that the energy lost is 45 joules. So going from the energy before to the energy after, I know that I'm losing 45 joules worth, which means the kinetic energy after should be 15 joules. I don't know the speed at A, I just know it's VA. So the kinetic energy formula, I write half m squared down. I know the mass is 3. And the velocity of this object is VA squared. And I can do something really similar for B. I know the mass is 2, and I know, well, I don't know a velocity, but I guess it's that. And these things should be equal. So if I tidy this up a little bit, it's going to be 3 over 2 VA squared plus B equal to 15. What's the equation I'm supposed to get? 3VA squared plus 2VB squared equals 30. Okay, so I've pretty much got it. I just need to double everything. Amazing. There we go. So those are essentially 2 simultaneous equations that I can use. This one and this one together. Hopefully I'll be able to solve something. Let's write them both down again. It's EV is 0. EVA squared. Oh, sorry, I forgot the squareds for this. Plus 2v squared is 30. Those are my simultaneous equations. Quite strange. I think what I would do, I would try and compare this to like situations that you've seen before. And I think what you've done in your AS Maths is you've solved things where you have like a line and like a circle equation, for example. So there's quadratic elements and linear elements in that. I think you've also solved lines and quadratic curves crossing. And the basic premise of it would be to make either x or y the subject of the formula. So something like this, x, and then sub it in the other equation, and then it gets rid of one of the variables for you. That's my plan going forward. I'm going to make one of these the subject of the formula. It doesn't really matter which. They're both going to be about as difficult as each other. I think what I'll do, I'll make VB the subject of the formula. So I'll take 3VA over and I'll divide by 2. And I'll get the formula that VB is minus 3 over 2 VA. And I don't know why I added a bracket. No need. Okay. That is what I've got. What I'm now going to do is I'm going to take this, substitute it in here, and that way my formula will not have VA in it. Sorry, it won't have VB in it anymore. It's going to look like this: 3VA squared plus 2 brackets minus 3 over 2 VA squared is 30. I'm terrible for putting this question in, aren't I? Sorry, guys. You gotta have some nasty questions, all right? Like these are all from the real marks, from the real exams. Let's see what this tidies up to be. So 3 over 2 squared, I guess. The minus is gonna cancel, so it's just gonna be this squared. Square in a fraction, square the top, square the bottom, 9 over 4. We also have to take into account that we're multiplying by 2, so I should probably just type that in on the calculator. That's the easiest thing to do. 9 over 2. Okay, very good. Let's try and work something out here. 3 plus 9 over 2 is 15 over 2. And right, let's solve this. Oh, sorry, that's still squared. Take the 2 up. Take the 15 down. And we get that VA squared must be whatever this is. 60 over 15. Oh, that's nice. That's 4. So A is, haven't quite figured out all the direction elements just yet, but it's either plus or minus 2. Now we're going to need to think about the direction part of it a little bit later on. But that seems like a nice answer, right? 2 meters a second. I think we can get on board with that. So now that I've got this, I'm going to plug it back into one of my original equations. This one will do nicely. And I'm going to put a 2 in. Okay, right. I think I see where this is going. So we're going to get minus 6 over 2, which is minus second. If I put in this as negative 2, by the way, it would have come out as plus 3. So I just need to make sense of my solution set for a second. So if we had A and VB, it could be 2 and minus 3, or it could be minus 2 and 3. Okay, cool. Is that it for that question? Solve the equations to find the velocities of each object after the collision. Oh, yeah, of course. They're colliding, right? So I'm just thinking of like what could possibly happen. So we've worked out that the velocities are 2 and 3, and it was A was 2. I'm going to get rid of the arrows for a second. B was 3. So they've collided, and we're trying to work out where they must be going. If they were still going that way, then that would imply that they were going to collide again. That doesn't make sense after the collision's already happened. So what must be the case is they need to go in opposite directions. Must have it bouncing back in that sort of way. So the correct answer set must be that A is minus 2 and B is plus 3. So let's just get rid of one of these answers. I think we need to get rid of this one, right? That is the true answer. Cool. That's the paper. Took me a little while to make sense of that very last bit. So there's a little bit of interpretation going on. Mathematically, just based on the equations, these two answers both held. But with the interpretation of, oh, these objects bumping into each other, we had to have it. We had to have that set. Hopefully this video is helpful for you in some shape or form. Sorry about the length of it, and sorry if it might be not quite as succinct as I would have liked. I'm tired making it. so everything takes longer. But yeah, hopefully it's been useful. Thanks, guys, and I'll see you all in January at some point. Take care of yourselves. Have a lovely holiday.